Hello, welcome to Functions Unit 8, Day 2, Instantaneous Rate of Change, also known as the derivative. So what we're going to talk about today is a lot about the average rate of change, which we have been doing since the beginning, pretty much, of the year. So average rate of change, we have our definition is f of x plus h minus f of x over x plus h minus x, right? Change in y over change in x. Or simply, we know in this denominator that the x's cancel, so it's just over h. And we looked a lot at secant lines versus tangent lines in the unit where we studied the average rate of change, right? And so we know that the slope between point A and point B, right, is found by this f of x plus h minus f of x over h, right? So what happens as h becomes smaller and smaller? So if your h becomes smaller and smaller, your average rate of change is going to become closer to the instantaneous rate of change. And so we're going to kind of look at that in this next graph below. So this graph here shows us that idea that if your h becomes smaller, so you're getting closer and closer to point A. So you start here from A to B, and then h gets a little smaller, right? Now you have this slope, right? Then you have this slope, right? And it gets closer and closer, right? And as it gets closer and closer, right, it gets closer to being the slope of the tangent line at A. And so what would happen if h became equal to 0? Well, then that we would have what we would call the instantaneous rate of change, or the slope of the tangent line. This tangent line slope is also known as the derivative of the function, so it has another name. So we can say the derivative of the function, we can say the instantaneous rate of change, we can say the slope of the tangent line. Those all mean the same thing. Some notations we have for it is f prime of x, y prime, or dy dx. So these are all the notations. We're going to mostly use the f prime of x notation here. So we have a definition then for derivative. So the definition for the derivative at any point x, using the idea that h is approaching 0, is this. So f prime of x is equal to the limit as h goes to 0 of the average rate of change. So f of x plus h minus f of x all over h. So this is basically kind of the same thing we've been doing all year, where we say find the average rate of change. We're just adding one more step, right? The one step we're going to add in is we're going to find the limit when h goes to 0. So we're going to substitute, right? We find limits by substitution. We just sub the value in for that variable. So we're going to sub 0 in for h, and that's going to give us our derivative. Okay, so next page here, let's go ahead and look at our first example. So we want to find the derivative f prime of x for the function f of x equals x squared. So from our definition before, right, we have to find the limit as h goes to 0, right, of f of x plus h minus f of x over h. So what we're going to start with is finding that average rate of change expression. So I'm going to take the x squared, right, I'm going to put x plus h in for x squared. So I have x plus h squared, right, minus, and then x squared over h. So this is a pretty simple one to start with. So what we do have to remember is what is x plus h squared, and we remember we've used this a lot throughout our time of finding the average rate of change, right? X plus h squared is x plus h times x plus h, so we get x squared plus 2hx's, right, plus an h squared. Okay, so this is going to expand out to x squared plus 2xh plus h squared minus x squared, all over h, right? And then we are going to cancel out our like terms. So here we have an x squared and an x squared that cancel out. And so what we're left with is 2xh plus h squared all over h, right? And then we can divide that h through. So this h cancels with this h, and one of the h's cancels here. So our answer is 2x plus h. So that is this part of our formula. So now we're going to do the limit as x goes to 0 of my expression I found, which is 2x plus h. Right? So finding limits by substitution. Oops, I made a little mistake. It's not x. Oh man, alright, that's h. So we're not putting a value in for x, we're putting a value in for h. So when we do our derivative, We're typically going to have an x in our answer for sure. So we're going to put 0 in for h, right? So we simply get 2x. So our derivative, f prime of x, is equal to 2x. So what does this really mean? What are we finding, right? We said, well, this represents the equation of the tangent line. So what I want to do is I want to draw the graph of x squared over here. And all right, so here is my graph of x squared. So what this tangent line, so the derivative is 2x. So if I am at the point when x equals 1, right? If I put 1 into this equation, 2 times 1 is 2. So that means the slope of my line at x equals 1 is 2. So if I draw that on here, rise 2, run 1, down 2, back 1, right? Here is my tangent line, right? If I want to go to, let's say, negative 2, right? 2 times negative 2 would be negative 4. So my slope at this point here, right, would be negative 4. So down 1, 2, 3, 4, over 1, or up, pen thing, stop. 1, 2, 3, 4, over 1, right? And we get this nice tangent line, right? And so kind of, you know, back when we were having you draw tangent lines, right, we kind of had you just guess parallel to the secant line. But now we actually know we have a way to calculate the tangent line and find the slope of that tangent line at that point. And we're going to do that a little bit later after we go through some more of these examples. Okay, so the next example, I went ahead and wrote a bunch of it out so you didn't have to watch me doing all the work, but we'll kind of just go through the work. So we're finding the derivative for 2x squared minus 3x plus 4. So again, we're going to put x plus h in here for the first term. So 2 times x plus h squared minus 3 times x plus h plus 4. And then we're subtracting f of x. So we're going to subtract the whole expression, 2x squared minus 3x plus 4. So we do our expanding, right? We know x plus h squared is x squared plus 2hx plus h squared. So distribute that 2 to each of those terms. So we get 2x squared plus 4hx plus 2h squared. Distribute this negative 3 to both terms, so minus 3x minus 3h plus 4, and then we have to remember to subtract each term, right? So minus 2x squared plus 3x minus 4. So those three terms all change sign. Then we cancel out our terms that cancel, so 2x squared and minus 2x squared, negative 3x and 3x, and 4 and negative 4. So we get 4hx plus 2h squared minus 3h all over h. Cancel the h's out of each term in the top, so that leaves us with 4x plus 2h minus 3. So the new part of this then is finding the limit as h goes to 0, right, of our expression 4x plus 2h minus 3, right? So limits by substitution, you put the value in for the variable, so 4x plus 2 times 0 minus 3. So this becomes 0, so 4x plus 0 minus 3 gives us 4x minus 3. And that is our derivative and our answer. Okay, so our next problem is find the derivative for f of x equals x cubed. So again, we're going to use our definition above, find our average rate of change. So we have to do x plus h cubed minus x cubed, right, all over h, right? Seems simple enough, right? However, we have to remember how do we expand x plus h cubed? So rather than writing it out, multiply times multiply times multiply, this is why we did the binomial theorem, right? Pascal's triangle. So if we have a binomial to a power of 3, we know the coefficients are 1, 3, 3, and 1, right? So our first term, we'd have an x cubed, right, plus 3x squared h, plus 3xh squared, plus 1h cubed. Okay, so this is one of the reasons that we did the whole lesson on binomial theorem to help us with expanding quicker for doing our average rate of change. So let's put that in here. So we get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Right, so cancel our like terms. Our only like terms here are the x cubes. So that leaves us with 3x squared h plus 3xh squared plus h cubed all over h, right? We have an h in each term above, so we can cancel that out. So our final answer here would be 3x squared plus 3xh plus h squared. All right, now we're going to find our derivative. Our derivative limit as h goes to 0 of our expression we found here of our average rate of change. Right? So if we substitute 0 for h, right, I think we'll kind of get the hang of this, right? What's going to happen with any of those h terms? We put 0 in. Right? They're always, 0 times anything is always 0. So we get our derivative is 3x squared. Okay, so this last one is a little bit messy. So we have x cubed minus 5x squared plus 4x minus 7 that we want to find the derivative of. So if we put x plus h in for our x's, we get our expression here, minus, right, our original f of x. We do have to expand x plus h cubed, so I wrote the expansion up there, and that's what goes for those first 4 terms. And then the expansion for x plus h squared is here. And then distribute the negative 5 to each of those terms, so you get negative 5x squared minus 10xh minus 5h squared, right? Distribute the 4 plus 4x plus h, right? And then make sure to change all these signs to the opposite sign. Cancel your terms here, divide everything by h, and so we get, oops, I forgot my signs here. So we get 3x squared plus 3xh plus h squared minus 10x minus 5h plus 4. So now we find the limit. So we're going to put 0 in for each of our h values, right? And again, what's going to happen when you put 0 in, right? Each of those terms that have h in them, right, are going to become 0. So this becomes 0, this becomes 0, this becomes 0. So our answer is 3x squared minus 10x plus 4, and that is our derivative. Okay, so the next thing we're going to look at then is determining the derivative at a specific value of x. So we're going to do the same process we just did. We're going to find the general derivative. And then if it tells us to find it at a certain value, we're just going to plug that number into the derivative expression that we found. So in the interest of time, I went ahead and found the derivative for x squared plus 5x minus 4, right? So same idea. If you need to, you can pause. And kind of do the average rate of change yourself, and then come back and see if you can get the same answer, right? Because the more you practice this, the better you're going to get at it. So we get our expressions 2x plus h plus 5. Find our limit. I keep putting x. All right, put h. We're going to put 0 in for h, and so we get a derivative is 2x plus 5. So this second step is just finding, right, the value at x equals 3. So we're going to put 3 into our derivative expression. So 2 times 3 plus 5. So this is 6 plus 5. So that equals 11, right? So our derivative at 3 is 11. So what this is going to represent then is the slope of the line, of the tangent line at x equals 3. And that's what we're going to look at next, is how to write the equation of that tangent line. Okay, so the last problem is kind of adding one more layer to this, and that's writing the equation of the tangent line to the function at a given point. So we know that the slope of the tangent line is the derivative, right? And so if we have the slope of the line, right, that's one part of writing the equation. The other part we need is a point, or the y-intercept. So if we have the original function, 3x squared minus 2x plus 4, right? If we want to find the point when x equals 1, we just sub it in and we find our coordinate point. Right? Our coordinate point is 1, 5. We then can find the derivative, same thing we've been doing. Again, if you need to pause this and look through the work, go for it. We get our derivative to be 6x minus 2. Okay? We use that to find the slope. So we put 1 into the derivative equation, so 6 times 1 minus 2. So this gives us 4. So that means the slope of our tangent line is 4, right? And it's passing through the point 1, 5. So at this point, we use point slope form of our equation. That's the easiest one to use. So y equals 4, our slope, times x minus our x value of 1 plus 5. And there we have the equation of the tangent line. And so it all kind of
builds up together. So this is kind of the longest kind of problem, but the most interesting of the ones that we have.